Hi, everyone. Before we forget, our team is really amazing. So unfortunately, not everybody can be here on stage, but they all deserve to be on stage. I've never worked with any team that was as excellent as ours, and everybody's so motivated. So please, hands up in the air. Applause for our people. And now we start with Tom and his instructions to get our Quick Lab account set up. So please go to this URL there, and I'll reach the microphone over to Tom. But you have to follow these instructions if you want to follow the hands-on lab in which you can actually run Driverless AI today on your laptop. All you need is a laptop, nothing else.
Hello.
If you could enable mic number 2. Otherwise, I'll go through it. So you just follow what it says here. You basically go to the URL. Quick Lab is spelled a little funny, so it's QWIK LAB. Quick Lab. And the prefix is H2O.ai, the subdomain. So you go to H2OAI.quicklab, QWIKLAB.com. And there you have to sign up. So you say join, you give your information, and you get an email that says click this link. As soon as that's done, you'll get back to that page, and you'll be able to log in. You'll see a catalog of choices, and there will only be one choice. And that will say Driverless AI and one GPU. That's what we need. And as soon as everybody is there, we can continue. If anybody has problems, please raise your hands, and we have people here in attendance that can help with that.
Okay. Are people getting in? Show of hands the people who did get in, and then show of hands the people that are having trouble.
So one more time, to follow these instructions, you go to h2ai.quicklab.com. Quicklab is QWIKLAB.com. You sign up by joining. You enter your information. You get an email. You click that confirmation link, and you'll be in the system in no time, where you will have access to this pre-built image that will run Driverless AI on a hosted machine that has a GPU and also, of course, a reasonably fast CPU. At that point, you'll just wait for our instructions to continue. So is anybody not yet there? Please raise your hand, and we'll give you more time. OK. So the website that you have to go to is H2O.ai, not H20, but H2O, like water, .QWIKLAB.com.
So it's H2O with a little o. It's not H2O. H2O.ai.
So water molecules have 2 hydrogen, 1 oxygen, not 20 hydrogens, OK?
So now lots of people are getting in. Show of hands if you're still trying to get in but haven't gotten in.
I think any browser will be fine, so it shouldn't depend on the browser or anything. We like the Chrome browser. Who has it working by now? About half. I think we have enough to at least have somebody around you nearby help you. It's basically just necessary for you to have access to this system to be able to run Driverless AI hands-on. You can always run it later. You can go to our website and download a Docker image that you can install with the instructions that are on our web page. And then you can also run H2O.ai even on your own computer. But it has to be a laptop with at least 8 gigabytes of RAM. It should be like a powerful enough machine. It can't be a small one. But we have it seen running on Macs, on Linux boxes, on Windows, everywhere. So I think we're good. So as we all know, there's not enough data scientists, especially not expert data scientists. Should I show you how to start the lab? Okay, that's a good point. Tom, I will let you all start the lab. So this is the lab. For those who haven't clicked on it yet, click on it. This will get you into this field. And here you say Start Lab at the top right, the green button. Okay? That's the most important button. Sorry about that. So if you press that button, you're good. Don't press it again. Just one time, make it become red. Once you click it again, it will stop it. Then you have to restart it. So now you have 57 minutes left of running this instance, but it has to boot up first. And while it boots up, I will talk, okay, about something else. So I need to be fast. That's why I was trying to get through it. But we'll get back to this website, and we'll copy-paste a URL that shows up on the left here. You see it here. This one you have to copy-paste, and then go to a browser, paste that in, and wait what happens. And at some point, you'll see this. And if it's already there and perfect, then we can continue soon. But let's not do that quite yet. Let me introduce the product first, because that was part of the agreement. So data scientists, we have a bunch of grandmasters and Kaggle masters in our company that help us devise these products. So we basically are making a tool that can avoid human error and automate some of the laborious tasks as model tuning, ensembling, automatic cross-validation, feature engineering, detection of time series, some things that are done over and over by people today, and some of them are making mistakes, and we want to avoid that. And in this example here, Andrew Ng has at least agreed to publish a paper that had a mistake in it just recently. It's important to not just sample randomly if the individuals in the data set are correlated to each other. In this lung image problem, you would have not memorized that there's a tumor, but you would have memorized the shape of somebody's lungs, and you would have said, oh, I know that this person has a tumor because there's 2 ribs there in that shape. And if you detect those same 2 ribs again, you'll say, oh, I remember that's a tumor. But it's not because there's a tumor. You basically just memorized the rib structure. So avoid making mistakes where the data is not random, but you pretend that it is random. So they had to republish the paper. It took them about, 10 days or so. And now it's corrected. But these mistakes should not be made because it's unnecessary. You can just have asked in the beginning, hey, are these rows independent or do they belong to something that groups them? And if so, provide me that column that tells me the grouping. And actually, the product has that fold column in there to avoid these mistakes. And InfoWorld said it was an Editor's Choice Award, so that's good. There's only a handful of these a year, so we are very happy about that. You can read that in more detail. And I ran it last night just to make sure that it still works, and it performed very well. Driverless AI got me to the 18th position out of 2,926. That's on a Kaggle challenge that has completed. That's no longer active, but still, all I had to do is click once and let it run. And I had a solution that was as good as like no one else, basically, other than some Kaggle grandmasters. 3 of which work for us. Those 3 pictures in there, if you can detect them, you get a free beer tonight. Basically, weeks, right? Weeks and weeks to get there. We just automated that part. So it's already a good product. In this Amazon challenge, that was the Paribas challenge, the Paribas BNP Paribas Bank. This is the Amazon challenge that's 40 years old. That was Marius's first challenge. He's now number 2. He was previously number 1 at Kaggle. And he told us that he basically uses this over and over. And when he joined us several months ago, he said, let me see that this works on Amazon. And from time to time, we test that it works. But we can't actually overfit for this data set because it's not our goal, right? Our goal is to make robust features. And we don't overfit. Every time we have a holdout prediction, it's very good. It tells you this is the accuracy that we think it will be on new data. And usually that holds up pretty well. So avoiding overfitting is an important piece. In this case, we're in the top 5% out of the box. But if you add a little bit of magic that Marius knows, you can be in the first percentile. And the magic is just to do one-hot encoding and adding a linear model and stack the whole thing. It's not that complicated. And even that we will automate, of course, because he works for us. We'll put that into the next edition. So it's always a little bit more work, and suddenly it's more accurate. Who would have thought? And the product also has automatic visualization. We'll go into that later, but the point I want to make is that this is visualization of big data, and you don't lose outliers. There's no sampling involved. There's no hex plots or something where you don't know exactly where is the point gone. The point is the point. And if there is an outlier in the 10 billion row data set, it's still there in this plot. And so that's a very good technique that Lee Wilkinson developed and we implemented. He actually implemented most of it himself. This is MLI, the machine learning interpretability. We'll get to it later in the hands-on session, so stay tuned. You want to know what your model is doing, otherwise you can't trust it, you can't deploy it, and that would be a shame, right? You won't deploy a good model just because you can't interpret it. So it's better to have a good model and have an approximate interpretation than an approximate model and know exactly what it's doing, at least in some cases. And this should help you get there. Another important thing that our customers are telling us, especially the H2O customers that are used to having a Java production code story, right? Every time you build a model, you have a Java deployment package that is pure Java, nothing else. It just runs anywhere. The same thing will be true for driverless AI. So all the munging, all the feature engineering, all the XGBoost models, pure Java deployment. And this is code that we have that works today. It's still in development. It will come out basically next month in January. And that's the architecture overall. So as you can see in the middle, there's some kind of brain. That's the driverless AI. But you can interact with it from many sides. So either you can tell it to do something, either from the GUI, as we'll see, or from the Jupyter Notebook or Python script. That's the client API. Or once it runs, you can look at it from your cell phone or whatever. Like I do that regularly. I just check it, right? It's basically just this client-server system where the client can be just a web browser. That's the GUI. But you can control everything from that. But you want to script it and automate it. So eventually you'll have scripts driving this system. That's why you want to have multiple boxes and multi-user management and all that stuff. And we'll manage that. I'll tell you that in the roadmap slide. But let's assume you have a model, like the ones I made yesterday to this Kaggle challenge. Once you have that model, you can deploy it. And what does it mean? Well, if the new row comes in of that data set that has some strings and missing values and numbers and texts, fields, and whatever, that row will then get transformed into the improved data sets that we made, basically, the feature engineered data set, and given to the model to make predictions. So the whole thing is called a modeling pipeline. We're not just talking about models, but we're talking about the feature transformation and the model and maybe stacking of models all in one as a full pipeline. That pipeline is an individual artifact, one of which is the Java version, as I mentioned. Others are Python versions. You can have a a Python pickle. That's what we have right now. If you were to download it from the product, you will get a wrapped pickle, which means it's a Python state that can be loaded back into this exact environment. So I can throw this pickle to my IT guy, and that department can just say, OK, a brand new box, a Python environment, put the pickle in and say go, and it will score any new CSV row or batch of rows, like a pandas frame. So there's no need for any GPU box or any runtime, anything. It's just Python at this point. But it should still be somewhat Linux, right? Because there is an XGBoost inside that has to be compiled. But we made it work for IBM. We could have a native version that works on a Mac, but not many people will have enterprise deployments on a Mac. So that's why you sometimes see us say, oh, okay, it's only Linux. Let us know if you have the requirements that are strict, but it wouldn't be too hard to make it run everywhere. But especially with the Java one, it will run everywhere. And if you have Java, you have Go, you have C, whatever you want. There's also a Thrift API. You can even use C# or whatever that Prithvi over there wrote. If you have questions, please just meet him afterwards. Basically, you can remote control the scoring system with a binary protocol anywhere. You can say, here, I have a row, please score it. And you send it over the wire. The other guy gets it, deserializes it, says, oh, this is the row. OK, let me score it, and sends back the results, either the transformed data or the actual prediction of the model. So that's all there. Imagine you have a, let's say, 2 gigabyte data set. You run all night on an 8 GPU box that you just brand new, like got an amazing box, builds 500 models overnight. You get a great feature engineering pipeline. At the end of that, what do? You don't have just 2 gigabytes. You have 20 or 100 gigabytes of data that you would like to score every night. So we will have a Java scoring logic, right, in January that you can put into Spark, for example, and you can score all these rows. But what if you want to retrain on big data? What if you wanted to fit that same pipeline on the 20 or 200 gigabyte data set? So the refitting of the transformer, that's on the roadmap for end of next year. So roughly 1 year from now, maybe a little bit earlier, we should have sparkling water as a backend for driverless AI so that you can have big data transformations. But I don't think we'll recommend it to go to train only on Spark. You want to have kind of the fast, rapid prototyping of figuring out what munging you need. And once you know what, then you run one time the fit on the Spark infrastructure with sparkling water and H2O GPMs and so on. You see the recipes coming in from the bottom. It's like a car manufacturing plant, right? There's an endless stream of ideas. You go to Kaggle, you see hundreds of recipes. People have ideas. They try this. Have you tried reinforcement learning? Have you tried LSTMs? Have you tried GANs? Have you tried extra tree classifier? Have you tried this and that? Percentiles, calibration of some things. You can do all these things as a recipe. And we want the data scientists to be empowered to write these recipes not in distributed Java, but in Python, right? Or whatever they like, or in R. And then be able to provide these scripts and we run them somehow. And we have to define that API clearly so that it's productive and scalable. But we don't want to over-engineer the thing and make it like 100% generic. But it should be just right so that it will make sense that you can build your building blocks. And we make sure that it's still not overfitting, and it's still fast, and it still runs on GPUs. So that's what we're roughly thinking in terms of complexity coming up. So this is the roadmap. You will see that now is, well, it's already there. We have a lot of features, right? We have the recipe of being good, basically at Kaggle-like data sets that are not images. We don't do images right now. So this is not a deep learning framework. There is deep learning inside, not in the version that you have, but next month's version will have deep learning inside for embedding categorical variables, certain features you can derive, or even for multi-class problems. When you have 100 different classes, it's easier to build one neural net than 100 times as many trees for a gradient boosting method. But it's not an image classifier program, okay? It handles texts. It can really have strings in it with like words and explanations, and it will do its best to do text-based features. But it's not an LSTM yet. That might be another recipe. We do prevent overfitting and leakage. We're very good about that, I would say. And we also have other things like the visualization and the interpretation, and this whole Python API. Everything is Python right now, at least from a user's point of view. But the Java module will come very soon. You'll see the multi-GPUs showing up more and more. So where you train one model, one XGBoost model on the whole DGX, let's say, with 8 GPUs. So where the data can be 50 gig distributed across the 8 GPUs, and you can build one massive model where the data does not have to fit on each individual GPU. Because GPUs only have 16 gigs of RAM. We might say, oh, that's small data. But actually, to train on 16 gigs is still a significant amount of work. And you will not be able to train 1,000 models to get to the best feature engineering pipeline. So there's a compromise today that if you want to have many models evaluated, then you can't train them in a way that is too slow, right? You just can't have it both ways. Unless you have a 100 DGX cluster, it's not realistic for most people. So we recommend going to something like 5 million rows or whatever it is for your problem so that you can run overnight, get good results, and then draw conclusions from there. Multi-user and data connectors, that's the enterprise features that we're working on. So having Hadoop connectors, database connectors, having security, you can log in. When you log in, you know the system knows who you are. And then you also have a Kerberos token, then it knows what you have access to. You get only the certain data sets you're entitled to see. Your colleagues can use the same box, but don't see each other's data and so on. That's all coming next quarter. And then a little bit more on time series. We already have time series support in there, so we do causality, conserving machine learning if you want. We're not cheating by looking at the future and saying, oh yeah, now I know what to do tomorrow because I already saw it. No, we're only looking at the past. But we're not making all the lag features and all the cumulative sums and so on automatically yet. That's in the code base, just not enabled. So that's a little bit more work for us to do. The user-defined recipes, or UDRs, as I guess we can call them now, they would be very useful, right? If you can just say, oh, what about random forest as a model, because I like random forest. That's the only thing you want to change. Or you want to change your loss function, or you want to change your the way how you do cross-validation. You know it has to be this way, and it can't be done any other way. Well, then sparkling water, as I mentioned earlier, that will be the big one. So if you go to docs.h2o.ai, you'll get all the information you'll ever need for anything. Like it will tell you how to install Driverless AI on your laptop. It will tell you how to install it on all the cloud vendors. It will tell you how to install it in the Nvidia registry, right? If you have a DGX, you have it in the registry of Nvidia. It will tell you all what about the settings for the knobs. When you start Driverless AI, there's a bunch of settings, and this will explain it. So I think we'll get to this right now. So who has it up and running already? Who cheated and clicked a little early? No. All right, let's see. Well, I did. Okay, so does anybody still have problems getting this up and running? Only a few? Okay, perfect. So actually, it looks like we're good. Only one person has a problem. That we call a statistical oddity. All right, so let's scroll down. I agree with these terms. I'm sure you read it. Did you see the typo somewhere? There's one extra word, H2O, here. Yes. That is there. We'll fix that at the next release. So H2O.ai or H2O, doesn't matter. It's just some password. That is to make sure that you know who you are. No one else knows who you are. Now you need to have a license key, and that you get from the instructions here. So you copy-paste this blob. Every single character here, copy-paste that over. Okay, so go back to the Quick Labs instructions, and you copy-paste that piece. It's just one long string of some garbled characters. That's your private key. That goes into this product, right into the GUI, where it says Enter License at the top. At the very top, you paste it in. Don't paste it in the bottom, paste it in the top. If you have an email with an actual license that you asked for earlier, then you can use your own license, because that one is tied to you as a user, which gives you maybe more permissions or something. In this case, I think the only benefit you get is If you have problems, you can tell us who you are and we'll be able to identify you. But for now, this is fine. Like, you just use whichever license you want. But if you go home, for example, you have to ask us for a license to get one. And you can ask for one, you'll get one for free, right? 30 days or something, no problem. We want you to give us feedback. So you save this license key. It should go away. And now you're in a good mode where nothing is in there yet, but we are able to start. Who is ready at this point? Lots of people? Perfect. Let's do this. Let's start with add data set. And let's go to the data folder. So right now you can still go into every folder on that box and like try to read plain text files that somebody wrote. We're going to make that more secure and not allow you to see everything. Right now we give you full access to your own box. But you could argue that someone else could do the same thing. So it's not yet secure. And we know that. It's just not yet finished. So go to Data. Go to Kaggle. And then go to Credit Card. And you will see the path at the top. Get the training data and say import at the bottom. The mouse has to go up and down a few times. If you don't know where to go, just go up or down. And then we'll add another one, and that's called test. So this is a good principle. You have two data sets, and if you give us both, we will never look at test, just to be frank up front. We will not use it. Even if it's a Kaggle problem, we will not use the test set unless the recipe shouts that out. Right now, we don't. Right now, what we do is purely training on train. So this 18th position earlier was training on train only. No test set, no distribution checker, no categorical agreement checker, no anything, no missing values, like imputation based on the global, this and that, nothing. There's no secret tricks. When we get the test set, it's the same results as if you don't get the test set. But still, you have it here, and we can actually pass it, and then at the very end, when the model is done, it will tell you what the score is on the test set, if it has a response in it. If it doesn't have a response, you'll just get the predictions for it, and you also get the munched test set. The munched test set is the test set that has the new features added to it, and the bad features removed, if you want. So we make the good data set for you out of the data that you have. That would be useful for further training if you want it, or whatever you want to do with it. So if you use this model, then we can do the scoring, but you can also refit outside. So we'll give you a transformed training set as well, which has out-of-fold created engineered features that are like not overfitting, but still valuable. And the features in the training data set that got enriched are smarter than just, let's say, a lookup table or something like it would be done on a test set. So we're doing batch-style munging to give you an enriched data set that's better than a row-by-row transformation. So you'll actually get a good data set out of this process. The training set that's enriched, you could actually throw this into another machine learning tool like H2O.ai and train more. But if you transform the training set as if it was a test set, row by row, you'll actually lose some information. Just to be clear about that, it's a small little distinction, but the act of turning your training set into a better training set has to be done on a full batch style, all at once mode. It can't be done row by row. But the test set is always done row by row, because it's like a real-time streaming scoring system, right? So there's a differentiation between transforming training and testing data. So if you're ever confused, ask us and we'll write a blog about it, because we have not done that yet, I think. So you click on train, it'll show you visualize or predict. Let's do visualize real quick. And this is now telling this internal Viz server, hey, here's a data set. Find me the outliers, find me anything that's unusual, find me anything that I should know about. and show it to me. That's for the top part. The bottom part is always shown. It's basically some kind of overview of the data, but not just like a row-by-row printing of the numbers, but some kind of meaningful way. So you can look at only spiky histograms, for example. And we'll show you something that's spiky. And there's only one, because there is no other spiky histogram of anything against anything. Everything else is not spiky. So it's good to know. Sometimes you'll see something unusual in here. And I think Leland is going to talk about this tomorrow. So you'll go to his talk and you'll hear more about the things that he's written down here from his own words. Okay, if there's people who couldn't open the GPU lab because it ran out, you have too many people attending, there's another one now, a CPU version, which is basically the same. It doesn't matter how you run it. CPU or GPU is fine if you don't care about the speed right now for the small data sets we're doing. So this is the automatic visualization. So that's nice. You can look at outliers. You'll only see things that are actual outliers. See, there's some points here that are interesting. The dot plots actually are fun because they're dropping the points exactly where they belong. It's not like a histogram where you have to make a same width bar somewhere. No, you're putting the point where it belongs. So this one is definitely some kind of outlier you should know about, and so on. It only shows you the relevant stuff, so that's nice. Okay, so let's build a model. Let's go to experiments and say new experiment. You can also do this from the data thing. Instead of visualize, you can say predict. And then you pick the training data set as a training data set. And you pick the test data set here as a test data set, just for later insights of how well we're doing. And now you have to select the target column. That's really all you have to do. And I will pick the last one, which is the chance of me defaulting next month is what I have to predict, basically. But this actual response has two levels, as you can see here. It has two uniques. So there's a yes and a no, or a 0 and a 1. And this says whether the person will default next month on their payment or not. And that's what we're going to memorize now in terms of a model that kind of makes the best guess. Given a person, will that person default next month? So this is a credit card default prediction model, binary classification. We can leave the rest as defaults, so there's no columns to drop. If you knew that there's some columns in there that you cannot have, then you can drop them, right? Then the model will never see them, as if you never had them. If you have an issue where the rows are not identically distributed and not from the same distribution, then that means that, and they're also not independent, so they could be from the same distribution, but they could be still dependent on each other. Then you would have to say, wait a second, I want to split the cross-validation faults where the same people are in the same fault. So I'm not cheating. I'm not cheating as in that example earlier. And that fault column you can provide. And here we have Mark Landry, by the way. Glad to see him. He's the guy I mentioned earlier in the other talk about the person that brought data science to the company was basically Mark. So hands up for him. If you have any questions about data science, he's very knowledgeable about all these little pitfalls. He has had many presentations about that, and you should read his slides. They're very good. And there's also a weight column, and they all have tooltips. So if you don't know what's going on, you should look at the tooltips. The weight column tells you the observation weight. Each event, each row has a weight if you want. You can provide a column that has that number. So now I will say go, but first I'll pick a different loss function for fun, like a log loss. You can do whichever one you want, but we also have a GPU here, so we can enable it, or you can disable it. If you click on reproducible, it will just make the experiment be the same every time you run it. That means if you want to know that it's going to be the same because you have a presentation tomorrow and you want your boss to see what's running live to be good or something, you can try that it works with reproducible on, and then tomorrow will be exactly the same. If you don't do it, then it will just be different. Now, you'll still get the seed that was used at the experiment. At the end, you will know which seed it was. So if you have a Python script, you can rerun the experiment with that seed. You'll get exactly the same results. But from the GUI, you don't want to type in seed, so we just made it like on or off. And this is the classification problem. I could say, no, I want to make a regression problem out of 0, 1. It's like my age. I want to predict how old I am or something. It's not really a yes, no. I know better this is a real age, but it's kind of weird if it's 0, 1, right? It's binary. So I think it's not a classification. It's not a regression problem. It's classification. So everything was auto-detected just fine. I'll take the log loss and I'll say go. Now this is running. As it's running, you'll see that it does something at the top. It says tuning backend. Oh, did something already. Now it's training 0 out of 8, 2 out of 8 parameter tuning model. So it's doing some parameter tuning at the beginning. First, it figured out the backend, which means it figures out if GPU works or GPU has a problem, then it runs on a CPU. Once it knows how to run, it will do some preliminary tuning, which is basically saying, figure out how to transform my response if it's a regression problem. Do I need to do a log transform or square root transform or something? And if it's a classification problem, like in this case, it won't have to do that. It can just tune the XGBoost parameters in this case. It will tune different depth, different column samplings, the row sampling rates, and so on, the standard stuff you would normally tune. And it already did that, and now it says it's starting with the feature engineering. So it has like a good model that it knows the data is reasonably well understood by this model. And now that we have a model, we'll keep the model the same. So the model parameters don't change, except the number of trees. So we do early stopping. Once it starts overfitting, we stop. We don't fix the number of trees. So even though everything else is fixed, we still let it converge until it's optimal, as judged by a out of fault holdout set, right? So it's all fair. We're basically doing early stopping on our tree building, and now we're building lots and lots of trees. Each model can have up to 1,000 trees or so, and we're building hundreds of these models. That's why GPUs are useful. Now, this is a very small data set with 20,000 rows. So if you're saying, oh, my CPU is actually faster than a GPU, yes, that's because it has to go over the PCI Express bus back and forth just to put in 20,000 rows and then run the algo in like 10 milliseconds or something. So don't judge this by small data, please. You can judge the accuracy, but even that, we don't have a small data recipe yet. So if you have a 100-row data set and you say, oh, look, this statistically is like my toy case, we might not do that well on that. Although, as Lee pointed out the other day, he had 2 Gaussian blobs and made a data set that's very difficult not to overfit, and we did not overfit. So we do use reusable holdout and other principles to make sure we're not overfitting. So in this case, you'll see now it's running, 2 minutes, 11 points, iterations down the line. Who sees something like this on their screen, just to make sure that we're all following here? Okay, great. Now we can tell you a little bit more about what's going on. So the top sections are just giving an insight about the progress, how many models so far. So 41 models and 764 features have been engineered and tested. The left side is the same as what you typed in the beginning. The right side is also what you said in the beginning, except that there's CPU and memory and GPU usage indication on the right. There's also a trace. You can click on the little trace button. You'll see basically what's happening. So each green thing is a GPU model. Each gray thing is some kind of method call. You can mouse over and you see what's going on. It's basically some kind of a real-time tool that gives you an insight of what's running. The red stuff is feature engineering. So every so often it makes some new features, then it builds a bunch of models, and then it does new features, models, and so on. This is how to figure out what features are good. And in the bottom left, you see the chart with the performance metrics as judged by always out of fault. So we're not showing the metric of training on the training data. Like we're not scoring the model on the training data and saying, look how low the loss is. We're only showing you validation scores. So every score you ever see will be an out-of-sample estimate of how it's doing on unseen data. But it could be done either with like a third of the data or a fourfold or something. It's not consistent how exactly the number is obtained. It's just the best estimate. Even if it's a 2/3, 1/3 split, you're still doing many, many scoring runs on samples of those data sets to give this reusable holdout principle a good run for its money, right? We're not making one number, we're making many numbers and giving you the mean or whatever we compute from it. So it's a good number. That's all I want to say. It's not just one test score somewhere on some validation split. It's a good number. It's what we think. This is how well your model does so far. And if you look here, we're down 30 iterations of this genetic algorithm. If you want to know more about the genetic algorithm, you can mouse over and it explains everything. There is a variable importance chart. Here you can see that the features are pretty widely ranged. So here this is pay times pay. So these are two different pay amounts are multiplied. There's a cluster distance after we segmented these three payment columns into clusters. And then you compute the distance to cluster 1. This could be the rich people or the poor people or whatever you want to call it, right? So you're supposed to not make these judgmental decisions in credit scoring or discriminate against people. This will tell you why. This is not a neural net that says the weight was 7.3. This is telling you really what is the feature. So we're reasonably well interpretable in this regard. And there's frequency encoding, cluster target encoding. So we have, first we cluster the data, then we make groups. But we say basically in each cluster there's these people belong together, and then we compute the mean of some other columns in all these clusters, right? And all of that is done with cross-validation, so it's all fair estimates. You don't want to have your own numbers computed with you in the sample. You want to compute it from other people that are like you. So all these things have to be done just right. And that's what the Kagglers are good at, otherwise they wouldn't win it, right? So that's the whole point, that all these little things are built in just right. Is anybody else having similar results? Great. Okay, perfect. So when this experiment finishes, you'll actually see that it will also build an ensemble. Now you might wonder, why 555? So what accuracy 5? What does it mean? Well, if you clicked on the help description right next to the 555 button at the beginning, you can click now, but in the beginning, when you're supposed to enter, there's a help. And you click that, you go directly to the web page, it explains to you what these settings mean. So 3 accuracy, what does it mean? 7, what does it mean? Roughly speaking, more means we do a little bit more cross-validation, a little bit more genetic algorithm exploration, a little bit more repeats everywhere to make sure that when we say this is a better model, it actually is a better model. So more conservative, a little bit more time-consuming. So even though you turn up the accuracy, not the time, it will still take longer. So that's not how long it will take, the time. The time is a relative time, okay? So the accuracy makes it take longer. Obviously, we know that, right? You can't have all high accuracy and fast. Oh, I want everything. No. It's high accuracy means it will take longer. The time is just a relative time. And I suggest always using time equals 10 and then stopping myself, because you can press the finish button at any time. That's the same as if you had set time equals 2 or 3 or something. Except that time 2 means 20 iterations, 3 means 30 iterations. If you manually stop at 17, there was no knob for that, right? So you're not going to get repeatable results if you manually stop. That's why we have these settings, so you can say, oh, I always want to run overnight with like 3 time. That's the amount of time I can tolerate. So it's more like your time tolerance given a certain accuracy. Now, the interpretability knob is not yet well exploited. We haven't done too many things. We have monotonicity constraints in GBM, but not, unfortunately, on the GPU implementation. So it's not really enabled. We have no linear models. That would be a very interpretable model, but that's all coming. So these will be new recipes that you'll see in the new year, where certain interpretability settings will mean actual different models. And then we can focus more on feature engineering, less on model tuning, for example, or training. So now that it's done, you'll see a bunch of buttons here. So you can either interpret this model, and I'll do that in a second. You can score on another data set, which means give me predictions of credit card default probabilities for each individual person in that data set, and that will come back as a download. You can transform the data set. you give your data, and back comes the munched one with all these features that we consider important here. You can also get the training data set out of fold predictions. Now, who knows what that is good for? Yes, you can do more model training with those out-of-fold predictions. You can build a meta model on top of it. That's called an ensemble, right? A stacking model, for example. So you can have, this could be one model. This whole black box could be one model, and it makes a prediction on both training and testing. And that's a new feature. You do this 10 times in a row, you get 10 columns. You throw another model on top, and it says, oh, these 10 columns, what do I do for each individual? And suddenly that becomes powerful. You do this with different loss functions in a for loop. You have 50 columns. You take a neural net on top, those 50 columns, you win Kaggle, basically. So it's not that hard. You can get the test predictions. That's what you want, usually. And then you can also just get the transformed training and test data sets. Basically, it's all there, right? You have logs. You can download the scoring package. The scoring package has both client-server, HTTP, JSON RPC, Thrift, everything in there, but also local node scoring. So if you have a Linux system, it will make a Pi virtual environment and run all the examples. There's examples in it that are random data auto-generated with the same schema as this data set. I can actually show that to you. Scoring package here. Oh, it's 80 megabytes. See, that's the whole transformers plus the whole models and the ensemble. Everything is in there. So if that finishes, I'll open it later. It's a bit slow right now. And on the bottom right, you see the summary of the experiments here. So you'll see it was a data set with 24,000 rows. We predicted a certain column. And this was the recipe. It did one internal holdout. And it computed the scores on that one internal holdout. So it split the data one time, and it computed the score on that split. But not just one time, but many times, and gave you a good estimate. It made 1,367 features. Who else has more features than me? Anybody has more? Who has less? Should be about even, right? Okay. Perfect. So we have some kind of distribution of features tested. So if you add this all up, we'll have probably 20,000 or 100,000 features tested just now. It's pretty cool. And who has a better score on the test set than 0.404? Less than 0.404, anyone? Okay, that's the power of luck, I guess. Awesome. So you see here the iteration 1 model in the training holdout was 43.4, and at the end it was 43.0. So not a huge improvement, only 4,000 improvement in log loss, but it's a small data set. We only ran it shortly. This data set is not very easy to squeeze information out, only 16,000 rows, right? Once you see it, you're done. Even the very first model is pretty good already. So it's not just a measure of how well does it improve, but how good is it in the beginning. That's the real judgment. And if you say, oh, my model is way better, then you shouldn't just think that it's better because it was better on your one holdout set or maybe your training metric or whatever. You have to be very careful that the estimate is a good estimate. So this iteration 1 estimate that I highlighted there is already a very well estimated number after we do the very smart feature engineering of target encoding already on the categoricals. Already handle missing values, already do all kinds of stuff with the transformation of the response if necessary. So it's not like a dummy model. It's not like the poor man's model first baseline. We don't have a recipe for that. People are asking, they say, we want to see how my model would have done or what would the random forest have done. We don't show that right now. We show only good stuff, basically. But even the good stuff can improve if the genetic algorithm yields better feature transformers that are useful.
So in yours and in mine, the last model is substantially better than the rest.
Good question came up from the audience. Why does it jump at the end? Why does it fall down so much? Well, that's stacking. That's the final model here that took 96 seconds, and that was 9 models trained. So it's 8 models and a final meta model. The 8 models are 2 different parameters, each 4-fold validation, and then they make 8 different predictions on the test set, and then the meta model puts them together. So this is already, it's in this case, it's actually blending with a linear blender. So each of the 2 components has a weight, and then they get put together. It's not half-half. It's whatever the linear blender deems right. We're not doing proper stacking right now, but that could be another recipe that we do a neural net or extra trees or something at the end, depending on what customers are asking. But I'm sure they're asking for higher accuracy is better usually. So that's basically it, except that we haven't done the experimentation mode and the interpretability, and we have Patrick Hall here, who authored the whole brains behind it. And if you have a microphone, I would really love for both Mark and Patrick to give a quick 2-minute summary of their work and their findings about it. Can we make that microphone live here? Good question. When you say finish, it will jump to the end and then do the ensembling and the deployment package, yes. So we'll always get the deployable model that's pretty accurate. You're just saying, I'm happy with the feature engineering so far. And you never know what's coming next. At any point in time, it could jump a lot. You don't know. That's the feature engineering for you. Unless you have like a base limit of what's in the data or something. Do we have a mic? Otherwise, I think you guys have to stand here. But
I don't know if it's on. Can you hear me?
yeah.
We're going to let them do just a few quick minutes. I know some of you really had a lot of trouble with Quick Labs, but you can use that key later on when you're at home. And I know that we have a lot of questions, so I told Patrick and Mark they have to talk very fast and 50 minutes so we can get to some of the questions really quickly, okay?
Hi. So I'm Patrick, and actually Navdeep, Gil, and Mark Chan, who are around, we'll be doing an hour-long hands-on just on this tomorrow. So I think that's the biggest take-home is tomorrow afternoon we'll be focusing just on the interpretability aspect. So if you're interested in that, please check it out. Just very briefly, our goal here is to be able to justify every decision that this black box machine learning model makes, so that we can show which features contributed to each decision that the model made, and to a certain extent, how much each feature contributed to that decision. And we do go so far as to attempt to write them out in plain English. So here we're saying so specifically for this person, we're saying something like their most recent payment status, pay underbar 0, was 2 months late, and that resulted in their probability of default increasing by about 35%. Okay? So we're trying to assign local variable importance for every single decision that the model makes, so that from that we can build reason codes about why the black box model is behaving the way it's behaving. And with that, I think I'll leave it off. I'll sort of give you guys that teaser for tomorrow. Come see it tomorrow afternoon if you're more interested in the interpretability stuff. And I'll reiterate, if Quick Labs didn't work for you, the key that you got in the instructions, you can download an evaluation copy and try it later, and that key should work for you.
Yes, the best way is to get a key from our website. That way it's longer lasting. It's a proper key. This is more like a toy key for this instruction here, but both will work for a few days or so. But the other one is the one that will long-term be with you. So get the one from your official request on the website.
I'll also be quick. Similarly, tomorrow I'm doing something that really kind of looks at these features, comparing some actual models I built. So I took my own effort without driverless, and then ran it with driverless, and once did both at the same time. So tomorrow, 2-ish, 2:30, something like that, I'll be doing something about that. So you can check that out, where we start digging into some of these descriptions you see here. If you hover over it, you see a really nice description. We'll work to improve that, but already is really nice to me. It may take a little bit of getting used to some of the lingo that is in there, and the documentation will actually help you. The documentation is really good if you can read what target encoding is. There's some powerful things in there that, while you're using driverless, we may assume you know, so we'll at least tell you what we're doing, but the docs will help you if you need to get up to speed with some of that. So tomorrow, we'll take a couple problems and tear those apart and look at the top features that are created and show that it actually tracks pretty well with some interesting concepts that I did myself. You know, I'd look at a problem, shift it around a little bit, and I was actually kind of impressed with what Driverless was doing with some complex interactions. The other one thing is that I found it to be very stable, and it improves as we've done some. I ran one a couple days ago where I had not put in a time series, and it was very overfit. I got an inaccurate loss coming out of the screen, and I come to check in with 1.09, not even today's 110, but and I thought everything was worse. But actually what it had done is it had done the proper thing. So we've encoded some pretty interesting stuff in there. Dimitri spent a lot of time on stability of these, and I found that that really works, especially for IID data sets. But now we're adding some time holdout methods so that even if you don't know where your data set is, but we detect that it is, we're going to help you build the right model, which is something that I'm personally passionate about. So do a little more about that tomorrow. So it sounded like we had a lot of questions. So I'm sure that we've got, I'm not sure the best format, we have about 1:50 left, but.
Okay. Oh, great. There's a question about the different components. So H2O GPU is a core piece to driverless AI because we're using GPUs, right? So there's XGBoost, there's truncated SVDs, there's clustering, logistic regression, linear regression, all these models are all implemented on GPUs now. And we are putting those into driverless so that everything runs a little bit faster. Deep water is more or less deprecated, as Shri said, so we're not really supporting it. If you want to do deep learning, we propose you use Keras or something like from Python where you're more expressive. If you want to just start and play with it, you're welcome to use H2O's deep water, which does have GPU support. But we're not really using Java to call TensorFlow C++, right? We can just call it from Python if we need to. So we will have TensorFlow in the product.
There was a question on there of where we can see what the transformations are. Are they just linear? And no, they're not. So that's, if the middle section right below the knob that's telling you how % complete, there's that feature importance. If you hover over each of those feature importance, you'll see that description again with the docs. So these are not trivial transformations. They're really good. There's some complex interactions going on. So yes, we do tell you that. And like Arno showed, we didn't quite download it, but you can actually download a data set that shows you the results of those transformations on both your training set and your testing set if you've provided one. So those are both important pieces of getting this done. And the system does tell you the output, and it tries to describe to you what it did.
So there's a file called features.txt that you get in the scoring package that explains all the features. There's names of the feature columns and then explains them in plain English. And there's also a variable importance column. So you can see which column is how important. And some of them are zeros. That's because they're still included, even though they're not necessarily picked up by that one final GBM model. But it's maybe picked up by the ensemble. So we're not dropping all the columns. So don't be scared if there's a zero sometimes. It's also an artifact of the genetic algorithm. We're bringing in a whole individual with a lot of genes in them, like a human. But not all genes are active and necessary. If you cut out a little gene somewhere, you're not going to just die, right? Basically. So the point is that these genomes, they're mutating and all that. Not all the pieces in there are 100% necessary. But the individual that's the best in the end has a lot of good stuff. That's kind of how you should think. Now this is the package, the scoring package, and you can look at it yourself, but it's all Python code. It's easy to go through, and basically download it, play with it. That's the takeaway message, and thanks for your attention.